Morning. Everyone can hear me all right, I'm assuming? Yeah? Okay. My name is Dominic Spill, and this is USBProxy, and it's the first half of this talk is going to be a little story about how I got here and a number of failed attempts to build similar devices and things like that. And then I'm going to show you what we built and hopefully demo some things. I don't know if anyone was in the lobby at 6:30 this morning, but that's when I finished my slides and then proceeded to write the demo code. So hopefully the demos work, but I know at least one of them was flaky. So I'm working on USBProxy at the moment. I also work for Great Scott Gadgets. So I work on Ubertooth and Bluetooth, Daisho, and unambiguous encapsulation. I don't work on HackRF, so don't ask me when it's coming out. And a couple of other little side projects that I've worked on. FCC.io is one I'm particularly proud of because it allows you, it's a URL redirector for the FCC ID lookups. So you should use that if you want to be able to copy and paste URLs to FCC filings. And there's another guy who couldn't make it, and I actually don't know how to pronounce his name. I think it's Stasiak, Adam Stasiak, and we met on the internet. And he's contributed, which is pretty much how I meet lots of men. He's contributed a lot of code to USBProxy, and previous sort of related things. He was doing some .NET stuff with FaceDancer, and his blog is Controlling Xbox. And his goal for this was originally to be able to inject traffic into his Xbox controller stream. And I've successfully distracted him into building an entire framework for this sort of thing. So in case anyone doesn't know anything about USB, it's that little interface thing where you plug stuff into your computer. It comes in a whole range of speeds. Low and full were USB 1, high speed USB 2, super speeds USB 3, and that's 5 gigabits a second. The device I'm talking about at the moment, we're mostly targeting the bottom three, low, full, and high. And Super Speed Plus is going to be 10 gigabits a second, is that right? And it's coming out in the next year or so. The spec's just been published. The only stat I could find for sales was from 2008, and you can pretty much assume that stat's only gone upwards over the past few years. And they're pretty interesting to security professionals and hobbyists. Everyone gets to write their own drivers, so you can be sure that a lot of them are low quality. Same goes for firmware. And then I'm kind of interested in what's going over the wire in between and how that's implemented and who's implemented those, the lower levels of the protocol. And my day job is building packet sniffers, whether it be Daisho or Ubertooth. So I thought, having not quite finished doing the Bluetooth stuff, we may as well just move on to USB and try that for a laugh. So I'm aware there are commercial Bluetooth sniffers. Now I've said that. I'm aware there are commercial USB sniffers. And I have used one, and some of them are good, and some of them are not so good. I'm just going to pretend they don't exist because they're not open. And statement that's incredibly popular with only half the room. But I don't know if, I haven't seen any of them that can inject packets or man-in-the-middle traffic, so they're not as good as my work. So part of the start of this came from FaceDancer, and I'm going to say everyone here is familiar with Travis Goodspeed's FaceDancer. Anyone not familiar with it? Excellent. Couple of hands went up. You may not be in the right talk. But I will try and explain it very quickly, and hopefully you don't need to know anything about how FaceDancer works to understand it. So it started with Sergey saying, USB isn't a bus, it's a network. And Travis took this and took a good fit and threw a peripheral chip on the front end and designed the FaceDancer. And you can use it to prototype USB devices in Python, and there's one there. I'm about to show a photo of one. I don't have one. I've never successfully assembled one. And you can prototype the device in Python, and he's got some good examples, and he's done mass storage, and he built sort of serial devices and things, all in Python. And NCC Group made a tool called UMAP, which is a host security assessment tool that runs on top of FaceDancer, which is pretty cool too. They look like this. And you can see 4 here have been successfully assembled. You can see 1 here that hasn't been successfully assembled. I have to say, this is not my photo of a failed FaceDancer. I was too embarrassed to take a photo of my failed FaceDancer. This one is courtesy of Snare. And you do have to build them, and I know you can buy them commercially now. I think someone's manufacturing them. But there are some other issues. So if you look at this diagram, the left-hand side is a good fit. And so there's a serial, like an FTDI chip, and then an MSP430, and then it connects to the Maxim USB device chip. And this makes it really easy to use from a host because it always appears as a serial device. You don't need drivers. There's no bootstrapping problem. If you build it yourself, there's no need to get firmware onto the in any difficult way because you've got a serial device immediately, so you can just talk to it from any host. And that's a really nice feature of the good FET and a really nice feature of FaceDancer. One of the problems is the interface between, I don't know if my math's right, between these 2 chips here, the MSP430 and the Max chip, is SPI, and it runs at 1 megahertz. And that means you can't support anything faster than that on FaceDancer. You have a huge latency going back and forth to the host over the serial connection, and you can only attack or investigate low-speed stuff. So a guy called Philippe Thuan, and I probably butchered his name there, created something called the RaspDancer that used the GPIO pins on the Raspberry Pi to increase it to 26 megahertz, which means we could at least look at devices that were compliant with USB 1.1 spec. And as far as I know, he designed it. I've not seen one. I've seen a sort of hacked up one he designed. I've seen the PCB layout, but I've not seen a real device. And Travis happened to tweet, hey, does anyone want to design one of these for the BeagleBone? And I did. And I should say, I have it here because there was only one. There are, like my FaceDancers, at least 2 failed attempts. But there's this one, and it plugs into the side of the, looks like this. It plugs into the side of the BeagleBone, and you can use the SPI interface and the GPIO interface from the host OS, and that really shows up my poor soldering skills. And you can control it. And it's entirely pointless. Because it's using an on-the-go IC, and the BeagleBone already has one built in. And this is the conversation that I had with Mike Osman. So backstory to this conversation is Mike had spent an entire weekend reviewing my PCB layout and encouraging me to go and build this thing. And then he waited like 2 weeks for the turnaround time for me to get it from Osh Park and get it shipped over to Australia and to solder it up and make it work. And then he dropped the idea on me that I could do the whole thing in software and probably could have been done weeks ago. And so I went off looking at other people who'd done similar things, and around this time, this was back in June last year, and an article appeared on Hackaday where a guy had managed to get Nicolas Boichat, I think, wish people had more pronounceable names, had written a Google Summer of Code project where he'd written this kernel module that allowed you to proxy traffic through the old BeagleBoards. And it didn't seem like many people had used it because the older BeagleBoards were relatively expensive, and it built against a 2.6 kernel, and only that specific 2.6 kernel. And I tried to get it working on the BeagleBone and port it to other kernels, and I don't know anything about operating in kernel space. And it was really complicated and confusing, and I decided I could probably write my own. So I thought, should I write my own kernel module? And this falls into the law of headlines. If they end with a question mark, the answer is no. If you look into the kernel code in the USB stuff, there's a whole lot of gadgets that exist. There's Ethernet, there's storage, there's serial, there are a couple of others. In general, if you've seen a device that, what you would call a computer that acts as a device, like a mobile phone, like an Android phone, it's using one of these pre-built modules. It seems like not many people write their own devices on top of this stuff. And I thought maybe it won't be too hard. But maintenance would be an issue because I could write something and then find that my kernel module was in exactly the same state as the one Nicola had written, and it was unmaintained, and no one was using it, and that's not really what I wanted. I wanted to build something that people could just grab and use. And while going through that, I found something called GadgetFS, and this is a file system. And it was written back in 2003, and I've not actually found any example of anyone using it. I mean, it is used, but if you, people have used it for various projects, but if you look online, you can't find sort of tutorials of how it works very easily. It's a couple of sample code programs on Linux USB.org, and I pretty much took those and worked from there. And one of the nice things about this is because it's part of the kernel tree, it's going to be maintained. If things move on, it will always build. I'll almost always be able to find it, and in fact, it appears by default in many distributions anyway. It's built as a module to exist there. So I thought this was a great platform to build on. And oh yeah, maintenance is no longer a problem except for the fact that we've had to patch it to make it work. But hopefully we can get our patch back into the tree, and again, maintenance will no longer be an issue. So I wrote a tool called USBMitem, MITM. It's about 1,000 lines of really, really hacky C. You've got to be careful not to actually look at it just when you use it. The only USB device it ever worked for was Ubertooth, because that's the only one I had at the time that I was testing with. And I sent it off to other people to use, and they're like, yeah, you know, this doesn't work unless you've got 2 endpoints with exactly these endpoint IDs and all this other ID stuff. But it was kind of a nice little proof of concept, and I, at this point, heard from Adam Stasiak, and he was looking to do something similar, and I said, why don't you go and buy a BeagleBone, and by the time you've got it shipped to you, I'll have tidied up the code, and it'll be fine for you to use. Probably guess that didn't happen. And we started exchanging emails about it and tweaking the code and things. And we decided, let's just start from scratch. It's a nice idea, but let's try and build it so we can extend it, and it's a little more usable for anyone else who might be interested in this, because we figured we can't be the only 2 people who want to proxy USB devices. So we built this C++ framework. It's a flexible and extensible architecture. It will have a plugin system. At the moment, the plugin system is you have to include the header file from whatever plugin you write and rebuild the library. But it will be a plugin architecture once I work out how to build that. And contributions are welcome. And it's based upon GadgetFS, and we use libUSB to talk to the devices. And it runs on the BeagleBone Black. And it will run on almost anything that supports GadgetFS. And one of the reasons I picked the BeagleBone Black is I forgot to put a picture of it in my slides, but it looks like this. And they are like $45. They are relatively powerful. They're a bit more powerful than, for example, a Raspberry Pi, and they're totally worth the extra $10. They have the on-the-go interface built in, and most of all, they're open source hardware. So you can go and download a ton of documentation, the schematics. There's all this fantastic documentation for the processor. So it's not just this black box like the one on the Pi is. It's really a fantastic platform, and it doesn't get anywhere near as much love as it ought to. So before I explain how USB proxy works, I'm going to attempt to demo something. So you'll see this is Wireshark, and there are some USB descriptors that have just come in from the host, and hopefully, if I start just hitting keys on here, you'll see the packets as the keys are being sniffed in real time, and you can tell from here, you should be able to tell that I typed a shift, but unfortunately, I can't type much without interfering with Wireshark. This is possibly not the best unit to demo with. Now, the way this demo is working is this keyboard is attached to a BeagleBone Black, which then proxies it through its USB interface to the host, and so it acts as a host talking to, sorry, it talks to this host, so I can just type, you know, and it appears, and those packets will have been captured in Wireshark, and then the way we're getting the data off the BeagleBone onto Wireshark on the host is through some really hacky scripts that I put together that pull it over Ethernet, and they use tail on a FIFO and stuff. But the plan is that at some point they will use the work that Mike Ryan and Mike Kershaw did on XCAP, which is extending, yeah, if I could find the patch, then it would have used it. But it's somewhere in my inbox. Let's just kill off those scripts. So XCAP is a really nice interface that we've been using for Daisho to extend Wireshark so you can sniff from devices that aren't network interfaces. So you can just pull in data in a PCAP format from any kind of interface, and it's really straightforward, and you can you just have to write like a settings language, so you whether it's a settings language, and you just kind of specify what possible settings your device takes, and Wireshark will handle building the UI for you so that you can start sniffing from those devices. So that's really cool, and they're hoping to have it in mainline Wireshark at some point in the next couple of months. So USBProxy is this library that just ships data around between the two interfaces. So there's a relayer that moves packets between the two interfaces. There's a manager which kind of handles all the setup and teardown and building the connection and creating a device model for us. And then we have these proxies on either end that we talk to the device and host. And they can, in general, I'm using them with GadgetFS and libUSB, but they could talk to anything else. So you don't have to use libUSB. You could talk to someone else. You could just talk to some code that generates a device in whatever language you want. And in the middle, we have filters and injectors, so we can modify and inject packets on the fly. So it looks a little bit like this. Obviously, the two outer connections to the host and device, they're USB, they're external, and then it just kind of ships packets around for us, and we only have to worry about processing the packets and moving them around and modifying them and whatever we want to do. So the filter's kind of nice. They just get given. You can specify which endpoint they sit on, or you can have them sit on all endpoints. We use them for logging packets in transit. So the Wireshark demo you just saw was, I wrote a filter that just logs in PCAP format, and you just pass it a file name and it just logs to that file. Or you can use them to modify packets, or you can just filter them out. You can remove them completely. So if you want a packet to just not appear at the host, or not appear at the device when it's called from the host, you can do that too. So let me try and... Okay. So what I'm going to do now is I'm going to use my filters on that I've set up here, and I'm going to proxy this keyboard to the host, and we're going to play around with the data on the way through. So what you're seeing on the host, this is the host system as passed through the BeagleBone, is but what I typed was ShmooCon, and what we did is we logged the key presses on the BeagleBone as we went through. I'm just logging them to standard out, but you could log them wherever you wanted. And then we passed them through a ROT13 filter, which just decodes the USB HID packet, and ROT13 is the character, puts it back in the packet and sends it on its way. And you can do almost anything you like to these packets because they just sit in the system until you're done with them, so that there's no time limit, and we'll happily take care of stalling the endpoints and things for you if you want to take some time over what you're doing with this packet in the middle, but you can screw with it however you like, or you can store them and save them for later and anything like that. So that's packet filters. And this is all you have to write to build one, is you have to just fill out. In fact, you don't even need the function at the front, the constructor. You have filter packet, and packet is just a binary blob. But just look at the USB spec for that. Just pull in the USB headers from the kernel, and you can decode that. And setup packet is mostly similar to packet, but it's a control request, which are just slightly different in USB from regular packets. And we just need to know the direction, because you don't always know the direction from the endpoint. So with a normal packet, you always know, based on the endpoint that it's going to, which way it's going, whether it's going from host to device or not. Setup packets, control requests, actually go in both directions, and they quite often look the same going in both directions. It's just, if, for example, you're requesting headers from your device, you might send it a header device request, a device header request, and you'll have that as 0 length, and then when it returns, it will have a length and it will have data put onto the end. And so we just need to know the direction. And they're pretty straightforward. The ROT13 one looks like this. I think that's it. It's not exactly very safe. I mean, that would completely screw up if I'd used anything other than an HID device, and we'd have done some really awkward things if I'd plugged in the Ubertooth or something. But it works for my demo, so. So another nice thing we can do is we can write injectors. And injectors slightly more complicated because we ended up with this system whereby you don't know if something's being injected, and there's some issues with blocking I/O, and GadgetFS doesn't support poll, and I can't remember the exact intricacies, but we arrived at something where you just write to a pipe for injecting, and we just pull it out of the pipe and throw it down an endpoint, and it kind of appears at the far end. So I'm going to try and demo this. So I've got an injector set up on here, and hopefully. So there's something not quite right with the way we clear the pipe, because I should only have injected one A character. Or I'm just failing at using netcat. But what you see going into netcat here is the endpoint at the start. This is the endpoint we want to inject on, which is the endpoint that takes data from the keyboard to the host. And then we have some flags, which are all just 0 when we want to inject and pass on the data. And then we have the length of the packet, and then we just have the data we want to inject. And that happens to be an A in HID. So we can inject data arbitrarily into the stream as and when, without us even having to touch the keyboard. So that's that demo. So that's the last demo that I know works. I will try and do the 4th demo, but I'm pretty sure it doesn't work. So the proxies that sit on either end, we pretty much use GadgetFS and libUSB to connect to the device and host, but you don't have to. You just have to have a host proxy and a device proxy. And in fact, at some point we're going to look at the idea of being able to connect 2 devices together and screw around with them in filters in the middle and things like that. But for now, you need one host, one device. And something we thought we wanted to do was have the host and device on various systems be TCP proxies, so we can stream or connect a USB device over a network. So this is my final demo, and I'm not confident. So we set up one end as the server, which is connected to my target system. Our definition of server and client are potentially backwards, but. And then we connect to client. Oh, that might help. need to connect my device to my client system. So here I have a BeagleBone Black that is only connected over Ethernet, and it's connected to now connected to my keyboard. And we will see on this other side that the descriptors came through. So we passed through the fact that it was a Dell keyboard through to the other BeagleBone, which is hanging off the side of my laptop here. And now, hopefully, if I go and type somewhere, something will happen, but I'm pretty sure it won't. Ah. Hey! So that is unexpected. My coding style is very haphazard, and that results in problems like this. What you're seeing here down the left-hand side is just the characters I was typing and just mashing the keyboard. One of the interesting things about this is they're actually not getting through to the host. So they're definitely getting from my client across the Ethernet connection to my server, at which point our keylogger is definitely logging them. And then our keylogger is going, well, I'm done with that, and throwing them away. So at some point, I need to work out. I think it's just a problem with how we're passing them around. I should state now, I should have stated at the start, this is incredibly alpha code. This is not code you probably want to go and run in a production environment, if it's ever going to be run in some sort of production environment. But I just wanted to come and talk about it here because I thought people would be interested. And if people got on board with it, then we might have a chance to develop it without us just developing it in our own little world and steering away from what people might want. So I'm really interested to hear anyone's feedback afterwards about what they think of the code, what they think of if they have any pull requests, it's all on GitHub. So writing proxies is also relatively straightforward. We have to implement connect and disconnect methods. We have to be able to reset. The is connecting into high speed, I mean, you've got to implement them, but to be honest, they're a Boolean, just return true or false. And then dealing with control request and send and receive data. And send and receive data actually work slightly strange, like the opposite way around to what you'd expect, because they come from the fact that we are talking to a device, and so send and receive are kind of swapped. It makes a lot more sense, makes some more sense when you stare at the code. But all you really have to do is define the descriptors, define the headers that you're going to see, so those things that you print out with libUSB, LSUSB, and in fact you can pretty much copy and paste them and put them into the structs and spoof a device, and the read and write functions. And that's all you need to do to be a device. And I wrote a loopback device, which I definitely didn't get working this morning, but all it does is throw data into a buffer and then pass it back to you. And it's incredibly simple. It's that long, plus some device descriptors, which are just a static block of structs that I define. And that's all it needs to be. And so writing your own devices and prototyping your own devices here in C++ is incredibly straightforward. And you just need to look at our header and then implement whatever functions we've got in there, but pretty much send and receive are the only two you need to worry about. So there's some slight drawbacks, and I should mention this now. The BeagleBone Black is amazing, and you should all go out and buy one, but we're not sure what kind of throughput we're getting. We know we're getting substantially higher throughput than FaceDancer does, and anything else that we've played with. But we're pretty sure that we're not getting 480 megabits because we're screwing around with things in the middle. So I need to do a bit more testing with that before I get anywhere to be able to look at kind of what disk read and write speeds we get through the middle of this and things like that. And a lot of that will depend on what you're doing with the filters in the middle as well. If you're just proxying the data and not filtering it at all, it does make it somewhat pointless, but that's going to be much faster than if you're modifying the data on the fly. As I said earlier, it would be nice to support methods of connecting, say, two devices together or to host together and sort of alternative layouts of connections. But we can't do that because while the BeagleBone Black supports 2 on-the-go ports, one is fixed as a host port and one is fixed as a device port. So the chip supports it, but the board doesn't. And the other thing is the chip supports a gigabit Ethernet connection, which would be really nice for monitoring 480 megabit traffic. But the PHY on the board is only 100 megabits. So ideally what someone would do is take the BeagleBone Black and take their open source specs and go and design something very similar that fixes these problems. Mike, please. So some future stuff. We haven't got any devices that support USB 3, although there are USB 3 device chips out there. We'll probably wait until we've got a working Daisho board because Marshall, who's down here, has been running a USB 3 core for Altair FPGAs for Daisho, and we're going to use that to probably do some of these tricks and integrate Daisho with USBProxy. It's supposed to be a shared library, and I haven't done that, and you're supposed to be able to use it from various places and from other tools, and at the moment it just all compiles into one monolithic binary, because that's how open source works. And we're on a configuration parser, so the idea would be, at the moment, I just throw in all the command line options into our tool for the demos I knew I wanted to run, but it would be nice to be able to just pick up some kind of config file and go, yeah, so I want to filter these packets, and I want to run this plugin against this endpoint, and so on and so forth, and some kind of nice config file that you can pass around to other people, and so people can share code and share plugins and things like that. We also like to put in some language bindings. I started writing some Python ones, but all they do is segfault. But they're this close to working, I swear. And they get into the Python, and then the Python causes the C++ to segfault, and yeah, that just, I don't know. So I've got nothing to demo on that unless you want to see it segfault. And I'd really like to have bindings for any language that anyone wants to write this stuff in. So if anyone wants to get involved, all you have to do is implement a device proxy or a filter proxy, filter plugin mapper for that language. Like, it's actually relatively straightforward. It's not a lot of code, I'm assuming, once it works. And I'm happy to help anyone with that, but I'm not sure I have the time or mental capacity to write language bindings for other languages. And once we've got and one of the reasons we're working on Python, and once we've got all that working, we want to write a compatibility layer to work with the existing FaceDancer code, because plenty of people have FaceDancer boards, and they can, they've written various scripts to go with these. There's some example scripts. There's that tool from NCC Group, and it would be nice to be able to apply them to the BeagleBone and use that to test things and operate those scripts at higher speeds than FaceDancer currently allows. And then also to be able to use them with all our packet filter and injector methods and things like that. And there are some interesting things we need to work out for that, but I don't think it should be a problem, such as just how we treat the device and how we interact with the device as a whole. Travis is pretty keen on writing the registers in the chip, and I'm pretty keen on just not caring what the chip is all about, and kind of trying to abstract myself away from that so that no one has to worry about what the hardware that it's running on is. So it's just two slightly different approaches, but we'll get there. So I wanted to say thank you to Adam, who couldn't make it, who's done a monumental amount of work on this, and has been really helpful in sort of suggesting the direction it's gone in. Travis and Sergey for FaceDancer and the sort of inspiration to get involved in this, and actually for being quite friendly and supportive about the fact that I want to say not quite nice things about FaceDancer. The other guys who worked on similar projects in the past, because while I haven't used either of them, I have certainly looked at them both and referenced them. And Mike for letting me spend my time doing this rather than working on things that actually make him money. Yay, Mike and his no profit. So think that's my final slide. The most important line on this is read the damn paper. I spent time writing a paper for the ShmooCon proceedings. Go and read it, and that goes doubly for the unambiguous encapsulation talk from yesterday. We put a lot of effort into that paper, and it'd be nice if we'd remember to mention that you should read it. You can find us on Freenode, and I'll answer questions there, or you can get in touch with me via any of these methods, and you can go and look at the code and laugh at the things I've written. And that's all online, and it's all open source. It's actually GPL-free for some bizarre reasons, but you can go ahead and submit pull requests to fix all my bugs if you want. Any questions? Not Mike Ryan.
Hi, I noticed you weren't messing with the CRC at all. I assume the BeagleBone Black handles fixing that if you like modify the data in the packet or something?
Right, we're above that layer with GadgetFS, so we don't have to worry about the CRC and things like that. So we're at just a slightly higher level up, which is also one of the differences between us and, actually I'm not sure what level FaceDancer operates at. It might be slightly lower than us. Yeah, so that's why we don't have to worry about things like that. No.
Now, I have two questions, but I'm only going to ask one. How did you need to use the kernel? Why couldn't you do it all in user space? I mean, what was not possible in user space that you ended up using GadgetFS and stuff?
Talking to the device chip. So the only way to interact with that is, there does exist, and we used like one line of code, which is the reason we're GPL-free, from something called libUSB GadgetFS, or Gadget. But I struggled to get that to work reliably, and it didn't seem to do much more than what GadgetFS would allow us to do. So we decided to use GadgetFS rather than that. But that also uses a kernel module because that's the only way to talk to the Gadget chip.
So you're still requiring your custom kernel patch, or?
I am currently still requiring the custom kernel patch, but I'd be happy to give it to anyone who might maintain a distribution if they want it.
I might know somebody
say
like
Pen
that.
2.
Thank you.
Any other questions? No? All right, you can find me later if you want to ask anything.